Black holes, these dense and enigmatic structures, are so powerful that not even light, the fastest thing we know, can escape their gravity. It's as if light, in its desperate attempt to flee, ends up trapped forever. The story of black holes begins with Albert Einstein's theory of general relativity, proposed in 1915. This theory revolutionized our understanding of space and time, revealing that gravity is actually the curvature of space-time caused by mass. Based on these equations, physicist Carl Schwarzschild described a point where gravity would be so intense that nothing could escape, not even light. Imagine a scenario where a star is compressed into a tiny point with infinite gravity. This theoretical concept was the first step in understanding black holes. In the following decades, the idea of black holes remained theoretical until, in the latter half of the 20th century, technological advances began to provide observational evidence. In the 1960s, scientists identified dense, compact astronomical objects that matched theoretical predictions. Then, in 2019, the Event Horizon Telescope revealed the first image of a black hole at the center of galaxy M87, providing visual proof of these objects' existence and consolidating decades of theory. Initially seen as theoretical curiosities, black holes evolved into fundamental elements of the cosmos, influencing galaxy formation. Discoveries such as Hawking radiation showed that black holes emit radiation due to quantum effects, adding a layer of complexity to our understanding. Today, these cosmic entities capture popular imagination, appearing in movies, books, and TV series, inspiring new generations of scientists and enthusiasts. The relationship between science fiction and real science is deeply symbiotic. In movies like Interstellar, the black hole gargantua is crucial to the narrative, with scientifically accurate representations based on consultations with theoretical physicist Kip Thorne. Another example is the Star Trek series, which frequently uses black holes to create dramatic scenarios and explore the limits of physics and space engineering. Black holes are not just narrative tools, but also powerful metaphors for exploring philosophical and scientific themes. They symbolize the unknown, the unexplored, and the limits of human understanding. In Interstellar, the black hole gargantua examines concepts of time and relativity, as well as the sacrifices humanity makes in the name of exploration and survival. In literature, Jorge Luis Borges's short story, The Aleph, uses a point in space that contains all other points, evoking the infinite density and singularity of a black hole to explore the nature of perception and existence. Alternative theories, such as white holes and wormholes, emerge as fascinating counterparts to black holes. White holes would be the opposite of black holes, expelling matter and energy instead of absorbing them. Imagine an inverted black hole, spewing out matter instead of sucking it in. Wormholes, on the other hand, are solutions to Einstein's field equations that connect two distinct points in space-time, creating shortcuts for near-instantaneous travel between very distant locations. Think of a secret tunnel that links two remote places, allowing you to traverse the universe in an instant. These theories offer new perspectives on the nature of space-time and information conservation. White holes, for example, could resolve the black hole information paradox, suggesting that information is not destroyed, but expelled elsewhere in the universe. Wormholes challenge conventional notions of travel and communication in space, suggesting that faster-than-light travel could be possible without violating physical laws. Black holes are regions of space where gravity is so intense that nothing, not even light, can escape. At the center of a black hole is the singularity, a point of infinite density where the laws of physics cease to function. Surrounding the singularity is the event horizon, the surface that marks the point of no return. Anything that crosses this boundary is pulled into the singularity. The curvature of space-time around a black hole is extreme, distorting the path of light and matter and creating intense visual effects. Imagine a stretched, elastic sheet with a heavy ball in the center, creating a depression. This depression represents the curvature of space-time caused by a black hole. The event horizon can be compared to a line around the ball, beyond which any object would inevitably slide inward. Another useful analogy is to think of a whirlpool in a river. The closer you are to the center, the harder it is to escape the current, similar to the increasingly strong gravity near the event horizon. The black hole information paradox is one of the greatest enigmas in modern physics. This paradox arises from the apparent contradiction between quantum mechanics, which states that information about a physical system's state should never be lost, and Einstein's general relativity, which suggests that anything entering a black hole, including information, is lost forever in the singularity. This conflict creates a dilemma about the fate of information when an object crosses a black hole's event horizon. One of the most intriguing theories to resolve the information paradox is the holographic principle. This theory suggests that all information entering a black hole is stored on the event horizon's surface, similar to information encoded in a two-dimensional hologram containing all the data of a three-dimensional image. This implies that the entire universe could be described by information encoded on a two-dimensional surface, challenging traditional notions of space and dimension. The study of black holes can inspire revolutionary technological innovations in space travel. Extreme physics and associated phenomena, such as space-time curvature and Hawking radiation, provide insights to create new propulsion and navigation technologies. Understanding space-time manipulation could lead to methods for bending or curving space, enabling faster and more efficient interstellar travel. These ideas, though still theoretical, open exciting possibilities for the future of space exploration. One of the most fascinating applications of black hole study is the concept of wormholes, which could serve as shortcuts through space-time, connecting distant points in the universe almost instantaneously. Although still theoretical, if we could stabilize these wormholes, they could revolutionize space travel, allowing us to traverse vast distances in short periods. Another technology inspired by black holes is gravitational wave propulsion. Gravitational waves, caused by massive events like black hole mergers, could be used to propel spacecraft at incredible speeds, surpassing traditional propulsion methods. Black holes captured human imagination long before they were scientifically understood. In ancient myths, the concept of a bottomless abyss devouring everything can be seen as a precursor to the idea of black holes. With scientific advancement, black holes found their place in modern pop culture, appearing in movies, series, books, video games, and art. In games like Mass Effect and Elite Dangerous, black holes are crucial plot elements and gameplay mechanics, offering challenges and mysteries for players to explore. In art, contemporary artists use the idea of black holes to create works that evoke the vastness and mystery of the cosmos. On one hand, black holes incite a deep desire to explore and understand the universe's mysteries. On the other hand, they symbolize the fear of annihilation and the unknown, capturing the imagination as entities that challenge understanding and evoke a sense of humility before the cosmos's vastness. Now we want to hear from you. Leave your opinions, questions, and theories about black holes in the comments. What would you like to know more about these fascinating cosmic objects? How do you think science and science fiction can continue to inspire each other? And don't forget to subscribe to our channel for more amazing videos about the universe's mysteries. Until next time,